the core of the question is sort of, so I guess you did answer it. You said that you never really gave it sort of a thought. You didn't have a preconception coming into physics. But I guess, being an undergrad, I sort of, and I guess people in the chat can comment on how they were. Being an undergrad, coming in, you talk, you watch like guys like Michio Kaku or sort of Sean Carroll, the big popularizers of theoretical physics. I sort of came in and I just thought that was all physics was. It's just beautiful equations, and you're just fooling around with them all day, and you think about it, and interesting, like, as you sort of go along in your physics education, you start seeing, well, actually, it's really interesting to do things like Taylor series expansions in a lot of physical situations, because it's because you're really interested. You have these really complicated equations that you probably can't solve for everything all at once in the sort of the general form. But if you're really interested in a specific physical problem, it's just, that's just sort of like the evolution of my ideas of like what it meant to do analytics. That sometimes, like, we're often very interested in very specific problems, and that's probably a big chunk of research is that, and that is certainly as worthwhile as in many cases as trying to find a general solution. But both are obviously powerful and useful.
Yeah, and I think that there's something here that's kind of maybe interesting to. By the way, Oil Franz, your comment in the chat, that definitely.
Yeah,
speaks to, I think, the experience of being recalls my own experiences as an undergrad, and I'm sure same for mine. I think there's an interesting question here about the relationship that we perceive between theoretical physics, mathematical physics, and what physics is actually sort of about and what we're trying to sort of achieve. I guess one take would be that, I don't think this is a very controversial thing to say, but I guess one take would be that the business of physics is the business of making predictions that are then verified in an experiment.
I think that's complete. I don't think there's anything controversial about that.
I think there's nothing too controversial about that. I think that some people would argue, and I think convincingly, that in addition to making predictions and comparing them to experiment, we want some sort of cohesive story that allows us to understand the connections between different experiments, the connections between different physical phenomena. I had a professor of quantum mechanics, Norbert Lütgenhaus, and at the beginning of our quantum mechanics course, he sort of described what he perceived to be the three phases of developing physical theories. And he said, the first phase is you gather data on the phenomenon. The second phase is you distill out some set of mathematical relations that can take data as input and make successful predictions. And the third and the final step is to distill from that mathematical framework a key set of physical laws or principles. This was his sort of picture of physics. I don't know if I totally agree with that as being the full story. I think that there's actually a lot of, and I'm sort of quibbling here because I'm not really qualified to speak on this. There's a sort of large school of philosophy of science that asks this question: what is science really doing? How does the project of science relate to the real world? And by the real world, I mean the external world, the objective world. How does science relate to truth, and so on? These are questions that people have discussed and debated for a long time. And it might seem like a sort of non sequitur to bring that up, but I think when we ask the question, what is solvable in physics? What does it mean to solve something in physics? What does it mean to explain a physical phenomenon in physics? This really is the kind of question that we're getting at. We're getting at this question of, like, what does it mean for a theory to work? What are we asking for from our physical theories? What is the sort of metric of success for a theory? For example, you were mentioning in the intro there that we call these models that aren't solvable non-integrable models. And I think it's interesting and kind of revealing of this point that even models that are integrable. So an example of this for the aficionados would be, for example, the spin 1/2 Heisenberg model.
Yep.
This is a model that can be solved by a technique called the beta ansatz. And in principle, this technique allows you to learn everything about the model that you're studying. Most specifically, it allows you to get the eigenenergies of the model quite straightforwardly. But the problem is that the computation of anything more than that, although in principle it is possible, is so difficult that if you're going to study that model, you're probably just going to use a Monte Carlo algorithm to study it.
Yeah.
And so, what does it mean to say the beta ansatz solves the model, right? In some sense, it solves it in principle, but in practice, the way you're actually going to work with this model a lot of the time is with something like a Monte Carlo algorithm, especially at finite temperature, where the beta ansatz is very cumbersome to work with.
So this is a really interesting point, and perhaps we could get into something sort of controversial here, because when you something that's sort of cooked into your education or the way a lot of people perceive physics is that the more like there's sort of like a hierarchy of contributions when it comes to things like solving the spin 1/2 Heisenberg model with the beta ansatz, or looking at it with like a very sophisticated Monte Carlo algorithm. Like there seems to be like a hierarchy where people assume that like the sit down and write the math down by hand is somehow much more important to the story. But I mean, like, all avenues of investigation, in my eyes anyways, feel equally important. So I wonder if you can comment, what's your take on the perceived hierarchy of avenues to research physics? And I don't think it's controversial to say that there are a fair amount of people who do say they share these feelings sort of out loud, and I think the literature reflects that as well.
I think that's a good point. I'm reminded of another professor's comment, James Taylor, astronomy professor at the University of Waterloo, and I remember once during a lecture he was bemoaning the fact that people don't think of numerical solutions as solutions. Yeah. And his argument was, of course, they're solutions. I mean, they're giving you the answer. That's what it means to solve a problem. And I think that the camp that is, I'm not going to say opposed to that position, but the camp that tends to be dismissive of numerical solutions is sort of the camp of people who are looking for a cohesive story.
Yeah.
I think there's a sort of prevailing sentiment, and I don't even know if the sentiment is really false, but there's a sort of prevailing sentiment that when you come up against a problem that you don't have an easy answer for, that is an opportunity to come up with some new idea, some new technique, some new mathematical technology to get you that sort of straightforward, clear answer and thereby elucidate new physics. So maybe an example that I could offer of this is that in modern condensed matter physics, I sort of alluded to this last week when we were chatting, we rely a lot on this picture of quasi-particles and collective excitations. So we imagine that the physics inside of a material, the ground state of the material, is kind of like the vacuum state of a universe with symmetries and dimensionality possibly quite different from our own, maybe a one or two-dimensional universe, maybe a universe with a sort of square lattice geometry instead of continuous spatial and rotational symmetry. And we imagine that the ways in which the material is perturbed away from its ground state, the ways in which it can oscillate away from its ground state, are sort of like particles living in this universe. And this conceptual framework opens the door to a whole family of perturbative approximation methods that we sort of import from particle physics with great success. We use these methods to, for example, correctly and very precisely predict the way that the material will behave at a phase transition. We use them to predict things like the response of the material to a magnetic field, to a neutron beam. And so, this set of techniques, this technological innovation, importing this technology from particle physics, doesn't just let us compute the problems, but it gives us a sort of coherent conceptual framework with which to understand the problem.
Yep.
Now, by contrast to that, if I'd never thought about that before and I just went ahead and did Monte Carlo on these systems, I would get the same predictions. I'd predict the magnetic susceptibility. I would predict the maybe the structure factor or some other quantity that an experimentalist might measure. But I would be lacking that conceptual framework that this analytic technique offers. And so I think all that to say that the reason that people sometimes tend to disparage computational solutions, I think, is really coming from this perspective that having an analytic framework to think about the problem in offers some additional notion of what's sort of going on, so to speak.